Okay, so this is the last lecture actually. So we will focus on whatever that is done in the class. Mostly we will focus on the series, and then as an example, the reason we are doing the series in the calculus course. I mean, in tail analysis, it's one of the main topic. But the reason we are doing in the calculus course is to do something called Taylor series, and mostly we will focus on the series, and then we will do some problems in the Taylor series. Okay, so let's see. But there is not much to do today, so we will see. Okay. So we start with we know what is the series, right? I mean, I'm not going to explain it. I will just write some of the theorems which we might going to use it. So one of the important theorem that we use is to, if you want to find the, so let's say you have two series, let's say alpha n, which converges to alpha. All of them are a series of real number, and you have another series, uh, basically not, yeah. So you have a series alpha n. Okay, so let me write n equal to 1 to infinity. And you have a series beta n. Here also n equal to infinity. This converges to beta. Then you still have this kind of algebra of limit. Okay, if you have, r uh, summation alpha n plus s times beta n, if you took, then that will also, so here I have to write here alpha n plus, let me write yes, beta n. So this will also converges to, so r alpha plus s beta. Okay. So this kind of algebra of limit whatever we did for a series, sequence, that also holds for series also. And of course, we know how do you talk about the convergence, right? Basically, you take the partial sum. So you have the summation alpha n. I say it converges if you look at the partial sum, which is basically, let me call it S1, which is just alpha 1, and S2, which is alpha 1 plus alpha 2. So similarly, you take Sn, which is summation alpha I equal to 1 to n. Okay, and then you see this series converges. Okay, so the convergence of the sequence is nothing but the convergence of the series of partial sum. Okay, so this is just I'm recalling it. Now we start with some useful theorems here. So if you want to find, okay, how do I say that the series converges or not? And there are some theorems which could be really useful. The one is the first comparison test. So right here, you have test for convergence. Okay, so the first one is, suppose you have let's say two series. Okay, you have an and you have bn. Non-negative times. To bn. See here, the non-negative is actually important, because if you don't have the non-negative terms, then you cannot actually guarantee, because otherwise there's no need that this series converges. I will tell maybe when we write it. Then what you have is, if you have this summation uh, bn n equal to 1 to infinity, if this converges, and then the summation an also converges. Okay. So here the non-negative is actually important, because if you don't have the non-negative, this term can diverge to minus infinity. So okay, I think there was can I please repeat my network? Okay, I'm not sure if it is your network or my network, but yeah. But I hope my network is okay. Okay, so what I was telling is this non-negative terms is actually important, because if you don't have the condition of non-negative, then even if you have something like this and Bn converges, that does not mean An converges, because An can diverge to minus infinity. So the non-negative kind of tells you that it is bounded by here 0. So this term actually converges. Okay. The reason this term converges, so you see, if you want to get the proof goes via the monotone convergence theorem. Okay, if you want to see it, because uh, it's a it's a term of a positive, see non-negative terms. So this, if you look at the partial sums, that will be a monotone sequence. Okay, and monotone sequence of positive number, and it is converges. So and it is bounded by this number. Okay, so basically the proof goes by monotone convergence theorem, but you need this boundedness prop. I mean, you need this terms to be positive and sorry, yeah, non-negative, and it is actually important. Because otherwise you can take an to be something like minus n or something. Okay, and bn is whatever the some convergent function you take, it will not necessarily work out. Okay, so this is the first one, and the second one is the divergence part. It goes exactly the same. If summation an diverges, then so the bn also diverges. So these are basically the tests that are in the sequence, and it's basically all the tests that you have in the sequence will kind of carry over to series also. Okay. Because basically series is nothing but a sequence of partial sums. So yeah. Okay. So let's move on to the next test. So a corollary for this. Okay. Sorry. So one of the corollary you can see is the following. So you said this L, which is basically the limit of n tends to infinity of an by bn. Okay, then we have the following. So basically, it's the limit comparison test. You use the limit. If you use the limit comparison test, you can able to get it. So the first one is if L is greater than 0, then what you get is bn converges if and only if an converges. So this is summation bn. I'm not writing the limit, but maybe we'll write the limit n equal to 1 to infinity converges if and only if summation. Okay. And this is when L is strictly greater than 0. And if L is equal to 0, then what we have is the summation Bn converges. Implies summation Bn converges. So these are the kind of the two tests that you have, but this is some form of the other one. You can prove it by using the limit comparison test. Yeah, but anyway, I'm not going to do the proof. I'm just telling, okay, these are the tests, you can use it. So let's move on to the one which can be actually very interesting, but let me see if you want to do some examples. Okay, so let's say we do one example at least, and then we'll move on. So we have seen the similar example already. So we here see one example. Okay, so let's say we want to compute this one, summation k equal to 1 to infinity 1 by k factor. Okay, so what do you think the limit of this? I mean, whether this converges or not. So how do you find it? So the answer is, you look at this one, 1 by n factorial, and this 1 by n factorial is actually less than or equal to 1 by 2 power n minus 1. Okay. So this is a identity. Let's say you can right now you can take it for granted. So if you want to prove it is not very hard, you just observe how many terms are here. If you look here to n factorial, you can see there are n minus 1 terms, right? So if you want to write as n factorial, this is nothing but 1 to 2 to etc. n. Uh, but but you see this 1 does not give you anything. So there are basically n minus 1 terms here if you leave the 1. And you can clearly see this is basically less than or equal to, sorry, greater than or equal to. So 2 times etc. 2. So I'm replacing, so here will be 3. Instead of 3, I'm putting 2. Instead of 4, I'm putting 2. So everywhere I'm putting 2. Okay. And so this number should be uh, less than whatever this number is, right? And this is nothing but 2 power n minus 1. Okay. And you take the reciprocal, you will get this inequality. Okay. Okay, now what is interesting about this inequality? So what you have is this series. Uh, so what we proved is 1 by k factorial. Yeah, exactly. So we can use the limit comparison test and we can prove it. Yeah, you're right. So this is less than or equal to. Okay, why this series converges? So why this series converges? So this is basically, if you remember, this is a, yeah, this is a Zeno series. Yeah, uh, Zeno series. Okay, I mean maybe that may be a different terminology. It's basically people sometimes call it geometric series. Probably it's Zeno who discovered it. Yeah, okay. This, at least this particular series is Zeno series. Okay, I understand. But generally, this is a geometric series. Yeah, in the stories of yeah, yeah, the Zeno paradox was there, right? The exact series came in there. Yeah, you are right. But in general, you can call it something called the geometric series, and the geometric series goes like this. It's a summation r power n. I think n equal to 0 to infinity. This is nothing but 1 by 1 minus r, provided the modulus of r is strictly less than 1. Okay, and it will diverges otherwise. Okay, so it diverges otherwise. So this series is called a geometric series, and you can see that this is basically a geometric series, right? So this, basically, you can see it as 1 by 2 power n minus 1, and of course this 0 is missing, but yeah, that doesn't matter much because there's 1 missing here. So Anyway, so what we have is because it's a geometric series, and this series is basically, if you want, you can even find what is its limit. The limit is 1 by 1 minus 1 by 2 minus 1, because uh, if you write the geometric series with r equal to 1 by 2 here, then you will have some 1 comes in the front. It will be 1 plus uh, summation n equal to 1 to infinity 1 by 2 power n minus 1. Okay. Wait. I think it's not a problem. Yeah. Because we are writing n minus 1, not n. Okay, so it will not be a problem. So if you want to change this n minus 1 to n, then you can start with 0. So it's not a problem. So yeah, so this is the geometric series, and hence it converges. Now you apply the limit comparison test, and you can prove that this one converges. Okay, and basically this number, whatever this number is called the exponential. This is basically the number e. It's not very important for whatever we're going to do, but yeah, that this is how basically the number e is defined, and one can prove that this number e will be lies between 2 and 3. E power minus 1. Mm, okay. Yeah. Okay. Yeah. It is e minus 1. Yeah. Not e power minus 1, but yeah, e minus 1. Yeah, because the e will be defined as, yeah, if you start from 0, then it is e. Since you are starting from 1, it is basically e minus 1. Yeah. Okay. So maybe start with the 0, so you can just write it as e. Okay, but anyway, maybe I'll write e minus 1. That's fine. Okay, so the number e is basically defined as a series of this form. Okay. And for some reason it appears everywhere, and hence it's very useful. Okay, so let's go to maybe one more example if you want. Otherwise, we'll move on. Let's see if I can give one more example. Okay, maybe we'll go to the root test. I think here I have example, but I don't know if I want to write that. Yeah, anyway, let's move on to next one. So you can use the divergence part also if you want. Okay. So this is called the ratio test. And it is also done in the class. I'm just repeating here just so that we can recall, and then we'll move on to the problem. Suppose here also you have a sequence of positive numbers. Okay. So here maybe I'll write. You look at the limit an plus 1 by an. Okay. So if, I mean, it's not necessary that this limit exists, but let's say this limit exists, then we can conclude. Then we have. So if L is strictly less than 1, then your series convergence. So the same thing kind of happens for the sequence also. But at that time you haven't done it, but you can look at any standard textbook that this kind of test there for sequence also. Okay, but usually it's interesting in series, but yeah, sequence also you can do. Summation n equal to infinity and converges. If L is strictly greater than 1, then the series diverges. Okay, so this we have done in the class also, but the thing is when you see here, if these two we have said okay whether L is less than 1 it converges, L is greater than 1 it diverges, and what about the L equal to 1? The L equal to 1 we cannot actually say anything about the convergence or divergence of the series. Okay, we will probably give example where both happen, both can happen. So let's at least divergence is easy. So L equal to 1 let's take, and you can take a series like your series A n is nothing but just 1. Okay, you take the series. Okay, if you take the series, what you can say is clearly a n plus 1 by a n. This is also 1. So this is basically real. And you can see that the summation a n diverges, right? Because you are keep on adding some number. Can I ask you one small thing? Because is this is done in the class, you have take the summation 1 by n, this diverges. Is this done in the class? Okay, it's done in the class, right? So, okay, we'll probably come back. Okay, so this is the ratio test, but let me just go back and give one more example here because I want to give one more example for diverges, but I don't know whether this 1 by n diverges is already done. So I didn't want to go and prove it's diverges. That's why I skipped it. But anyway, let me do one more example and go. So you look at this series, okay, 1 by root n. So n equal to 1 to infinity. So one may ask, okay, what about this series? Is it converges or diverges? Okay. So what you can do is you can compare this series with some other series that you already know. Okay. So this is basically n equal to 1 to infinity 1 by root n. Or maybe we forget this thing for now. Okay. Just take this and you can see this is less than just n, right? 1 by n. Sorry, this is greater than 1 by n. Why? Because root n is less than or equal to n. And hence you take the reciprocal, then the sign will change. Okay, and this is true for all n. And now you can take the sum. So if you take the sum 1 by root n, this will be greater than sum 1 by n. And we know that this series diverges, right? So thus by limit comparison test, what you can say is the series diverges. Okay, so I will just show it here. So this is what we have. We have a sequence an which is less than bn. So if an diverges, then the bn will diverges, and also if bn converges, an converges. But uh, The hypothesis is both of the an and bn are non-negative as non-negative terms. Okay. So here all the hypotheses are satisfied, and we have this term diverges, and hence a series which is larger than the 1 by n series also diverges. Okay. Thus. Yeah, I put L. Okay, maybe I just don't want to write it. Okay, so for L, okay, now we move on to the ratio test, and you can just recall the ratio test. We are looking at the limit an plus 1 by an, and we call it as L. If L is less than 1, then your series converges. If L is greater than 1, then your series diverges. And when L equal to 1, you cannot say anything. But what we have done so far is when L equal to 1, we established there is a series which diverges. Okay. Later I will show you there is also a series which converges. So basically at L equal to 1, your test will fail. Okay. Before going to that, maybe I will do one more theorem. So this is called Cauchy's root test. So it's a very standard one, so, but we'll just write it here so we can recall. So here also, see, it's not necessary that you always get this kind of limit exist, but we are assuming that a limit exists. So here also, if this L is strictly less than 1, then your series will series summation. Which is okay. So this is all we have. Here also, when L equal to 1, we cannot say much. Okay. Okay. So at least here you can see, right? This positive term is actually very important because otherwise, you cannot take the square root. But I'm not very sure that whether we need a positive term here. You may not exactly need a positive term. So at least when I see the proof, the positive term is not needed. You need non-negative term so that this, nth root makes sense. Otherwise, nth root does not make sense. But I'm not very sure you need a positive term or just non-negative term is enough. Okay. But as long as I read the proof, it doesn't seems like positive. The exact positive is not needed. You can just have non-negative terms. But anyway, at least for positive term, it is true because I take it from the book. Uh, So you can verify it one times, but I have read the proof and I don't think positive is needed exactly. Okay, so let's move on to the examples here. So let's do the same example, but a little bit differently here. So we look into infinity. Let's look at x power n by n factorial. Okay, it's the same example what we did before, but just put a x here. Okay, so this is your sequence, and x is fixed. Okay, x is some real number. Now the question is whether it's converges. Okay. So here also what you can do is you apply. See, here you can directly see which is easier to do is to apply the root test or ratio test. So the easier to do is to basically apply the ratio test, because the root test means if you apply, you will have something like nth root of n factorial, which I don't know how to handle. Okay, so you apply the uh, ratio test. Okay, so here L equal to nothing but limit of an plus 1 by an, which is x power n plus 1 by n plus 1 factorial divided by x power n by n factorial. So, but this is nothing but x by n plus 1. Okay. Now you have to take the limit as n goes to infinity. So as n goes to infinity, this term will be 0, right? So your limit is basically 0. So since your limit is 0 by ratio test, you will get so L is L is equal to 0. So by ratio test, your sequence is a convergence. So here, yeah, that is true though. Terms are not necessarily positive. Let me just go and check here. Here I'm writing for positive terms. See, you are right. Actually, the terms are not positive, but what you can do is you can take this modulus and you can still apply the test. Okay, there is something called absolutely convergence and conditionally convergence. So if a series is absolutely convergence, then it will always be conditionally convergent. So what you can do is whenever it is negative, you always take apply the modulus, and you can kind of take the uh, obviously if the x is negative, what you can do is you apply the modulus of this. Okay, instead of taking x power n, you take the modulus of this. That is called something called absolutely convergence, and you can use the ratio test to compute the absolute convergence. Okay, once some series is absolutely convergent, it will be convergent. Okay, probably since you have asked, maybe I will write what is absolute convergence. So is it done in the class? The absolute convergence is done in the class. Yeah, it was mentioned on this. Yeah, I didn't see much in the paper, but I will write here. So you have this series. A series, you take summation n equal to 1 to infinity, and you take a an. Okay. This is said to be so absolutely convergence. Sorry, said to converge as absolutely or absolute. Yeah, however you want to write. I will use the same thing. Absolutely, if the summation n equal to 1 to infinity, absolute value of an, this converges. Okay. So why do we care about this is because of the next theorem here, which says that absolutely convergent series converges. Okay, so in some sense, if you have a series which is absolutely converges, it will be converges. Okay, and when you want to do the absolute convergence, you are taking the modulus of this, right? And these are a series of positive terms, and for this you can use ratio test or root test or whatever. Okay, so that's why I mean here I'm skip. I mean I'm not writing. If you want, you can put a modulus here, but for negative term, it just comes with a minus here, and this minus and minus cancel out, and you will end up getting the same thing again. Okay. So because of this, you can actually use. Okay. So this theorem, I'm not proving it, and I don't know if the proof is very easy. Maybe the proof is easy. Yeah, the proof is easy. If you want, I can give the proof also. Do you want me to write the proof? But it's not done in the class, and if you want to see, then I can. Okay, then we can do the proof. So what you do is you do the sigma n. So you consider two terms. You take Sn and sigma n. Okay. So what be the, and maybe I'll write here since we are writing and you can write. So this is basically partial sum here. Summation I equal to 1 to n uh, an, and let's say sigma n is nothing but summation I equal to 1 to n absolute value of n. Okay, so I have two terms here. Now just 1 minute. Hey, do you know this, right? Every Cauchy sequence is convergence. Do you know that or not? Okay, then I can use that. So every Cauchy sequence in R is actually a convergent sequence. If you change the space, then it is not true, but it is true in R. Okay. So then what you do is, so I know that sigma is convergent, but now let me look at what is the Sn. So we look at the Sn minus Sm. So what we do is we prove this. We want to prove that Sn converges. Instead, we prove that Sn is Cauchy. Okay, and that is enough to tell you Sn is convergent. Okay, this is nothing but a modulus, j equal to m plus 1 to n. Uh, I think it's n, right? And I will write aj. And now you just apply the triangle inequality. I mean, multiple times you have to apply the triangle inequality, and you will get j equal to 1 to, sorry, m plus 1 to n aj. And this is nothing but sigma n minus sigma n. Okay. So what we have is this series is Cauchy, and this term is, it's kind of less than this. So what you have is, this is also a Cauchy sequence. Okay. So basically, this is Cauchy means this is a less than epsilon, and you have all this epsilon delta thing, right? And you just have to write it, okay? Uh, since this is since sigma m is Cauchy, so this will also be Cauchy sequence. So is it clear, or should I say it properly? It's clear, right? Okay. Because the sequence is Cauchy if for all epsilon there exists a n such that this term is less than epsilon, right? So, and similarly here we have to prove for all epsilon there exists a n. You take the same n which happens for here, and you can clearly see since this itself is less than epsilon, this term is also less than epsilon, and you prove that this is Cauchy. Okay. Since sigma n is Cauchy, Sn is also Cauchy. Less convergent. Okay. So that is all. There's not much here. Okay. So the proof, if you look, it's actually very simple. But if you look at the converse is not true. Okay. Because here we used the triangle inequality. The other direction is not true, and here you can see the converse of the theorem is false. So can you quickly try an example? It's not very hard. Converse of the theorem is false. Oh, I don't know if you have seen the example. 1 minus 1, 1 minus 1, okay. Is 1 minus 1, 1 minus 1 is even convergent. It's in some sense, if you look at the partial terms, right? Partial terms will goes like 0, 1, 0, 1, 0, 1, 0, 1. So it's not actually convergent. Yeah, it's wrong, yeah. But you're almost there, okay? You take this one by n, okay? You take this one. We didn't give a tool to prove it is convergent yet. At least I hope it is done in the class. Uh, there's something called alternate series, which is, I think it's done in the class, if I'm right. So you can see this series converges. But if you look at, we just know that if you look at the summation 1 by n, this one diverges. Okay. So that's pretty much the example, and this one we will come back. Okay, so this is something called alternating series. We will come back and tell when it is converges. Of course, I don't think I will give the proof, but at least we will give the theorem. Okay, so let's move on and try to see if we can do a little more examples. So yeah, so I think I kind of answered your question here. Even though these terms are not always positive, what you can do is you kind of look at the absolute convergence. Okay, so when you look at the absolute convergence, you can apply the ratio test, and if your x is negative, then the absolute value if you take it will be nothing but minus of this, right? Uh, and that minus and minus will kind of get cancelled, so you don't have to worry much there. Okay. It will be minus if depending on the n actually, but just give me a minute. Yeah, depending on the n, yeah, here okay. If n is even, what happens? Uh, this term will be positive, but this term will be negative, so you will have a negative here. Okay, that is there, but it still doesn't really matter. So it will be some negative x something comes mod x to n mod x to the n is x to the n mod. okay, you are telling this, okay. Mod x to the, okay, mod x to the n is basically x to the n. Yeah. Yeah, mod x to the power n is x to the power n mod. Yeah, this is true. Yeah, I mean, I applied that. That was not my problem. My problem is it depends on whether it is negative or positive. That's what I was thinking. Because depending on n is whether odd or even, the parity will change. So I think you will always get a negative sign here. If you have a x is negative, you will always get a negative here. But it doesn't matter because your limit is 0. So minus of 0 is just 0. Okay. If your x is negative, then you will get minus this, but it will be 0. Okay. So you mean you have to go back and use the absolute convergence to do this, but for all our purposes, I mean, yeah, it will work. Okay, and we have also seen that you just have to go and find that absolute convergence of this. Okay, so we're here. Yeah, you try to check the absolute convergence, and for the absolute convergence, you can use the ratio test. So that was the idea. Okay, I hope I answered this. So let's move on to the next problem. So this is also a problem in root or ratio test only. Okay, just give me 1 minute. What's the time? Yeah. Just looking at the time. So now we look at the series here. Summation n equal to 1 to infinity. N by 2n plus 1 power n. Okay. So do you think it's a convergence or divergence? No, all diverges, yeah. Maybe you can take a minute and think, and we'll do. So let's do the problem. See, what you can see is you have converges. Okay, great. So what you see is you have the power n. So here the ratio test will suffer, because if you do that, then there will be a power and there will be a power in the denominator. Okay, and that will not be easy. So what you do is you apply the root test. Okay. So if you look at a power, an power 1 by n, this is nothing but n by 2n plus 1, right? And so you can write it as a little bit like 1 by 2 plus 1 by n. Okay. So I'm basically multiplying and dividing by n on both of the terms. Okay. Or, yeah, so this is what I'm doing. Which is same as saying multiplying and dividing by n. Okay. So when you do that, what you will get is this actually tends to 1 by 2. Okay, which is less than 1. Now you just apply the Cauchy root test, and then you will get it. You can just, okay, so I did it using ratio test. Okay, maybe we'll try using ratio test also and see. I feel root test was easy, but let's try ratio test. So if you want to look at this, it's n plus 1 by 2n plus 2. whole power n plus 1 divided by n by 2n plus 1 divided by n. Now what you do? I mean, are you going to estimate something and do it, or are you going to directly do it? Yeah, okay. Uh, because from here I don't know how to do it. Okay. So whenever something comes in the power, you try to see which one will be easy. Okay. Sometimes most of the times I feel root test should be easy. Yeah, yeah. You can give. You can wait for a while. Okay. Maybe give me a minute and I'll join back. So you can try for a minute and we will come back. Okay. I will stop the recording for now and I will join after a minute. So you can let me know once you are ready. Okay. Yeah. Okay. So did you got it? Okay. So maybe if you want, you can discuss towards the end. Okay. If yeah, so that whenever you say, I can write it down. Maybe we'll continue with this, and probably I don't know how much left. I mean, there's not much to do here. We'll do some test and then we'll do some Taylor series. Okay, that will be interesting. Some of the Taylor series things are interesting. Then probably the last 15 minutes or 20 minutes you can ask me. So we'll do some 40 minutes, some problems, and then you can ask me. Okay, then we can continue now. Because most of the things, what happens is you either have to use a root test or ratio test. Sometimes yeah, you might use something else, but mostly root test or ratio test. And there's something called, see, you have seen some 1 by n power p, right? So that also last time we did, right? So this will also kind of come into picture. So only that much is there. Okay. So let's do one more problem here. Hmm. Okay, maybe I'll just give me a minute. Yeah, so I will write another problem. So third problem we'll write. So this third problem is basically something. When I write it, it will be clear. So if you look at n into n plus one, so this is my problem. So what we can do is okay, we can try to apply the root test and ratio test, and so let's apply the ratio test here. An plus 1 by an. If you look here, this is nothing but n plus 1 times I think n plus 2, right? It's 2 by n into n plus 1. And you can try to take the limit of this, and you can see this tends to 1. Okay, because this 2 will cancel out, and this is just nothing but 1 plus 2 by n, and this goes to 0, so the limit is 1. Okay, so you have now you have a series whose limit is 1. So here you cannot use the ratio test, and similarly you can apply the root test also. uh, it will goes to 1. Okay, So the ratio test and root test does not works here. But let's see what happens to the convergence of this sequence. Okay, so you might have known something called a partial fraction, right? So which we have done it when we did the integrals. We have done the partial fraction. So we are going to do the same partial fraction here. If you look at 1 into k into k plus 1, and if you do the partial fraction, you will get this is nothing but 1 by k minus 1 by k plus 1. Okay. So I'm not going to the steps here how we got it because we have done in the last class. So basically what you have to do is something like, if you have something like that, I'll probably just give the idea here if somebody watch the video. So you write this as 1 by a by k plus b by k plus 1, and then you equate it. Okay, so this will be 1 by k into k plus 1, and if you compute, what you get is 1 is nothing but k plus 1a plus kb. Okay, so this is what you get. Now from here you need to find, okay, what is this a and b. Okay, and once you find what is the a and b, then you can write like this. But anyway, it is right. What I said is there. Okay. So we have this. Now if you look at the sum of this, so if you want to just verify, all you can do is just cross multiply and see. Okay, this will be k plus 1 minus k divided by k into k plus 1, which is nothing but 1 by k into k plus 1. Okay. If you want to verify, that verification is easy. So now you take the sum on the both sides. It's 1 by k into k plus 1. So this is nothing but summation 1 by k plus, minus summation 1 by k plus 1. Okay. So where your k runs over k equal to 1 to n. So what I'm doing is I'm trying to find the partial sum. So let's say I find the partial sum Sn of this term. So you have this, and but if you see here, what happens is most of the terms get kind of cancelled, right? Because here first term it's basically n. Okay, maybe I'll write here because it's the first time you're doing it. It's 1 by 1 by 2 plus 1 by 3 to 1 by n, right? Minus, you start with k plus 1 there, so it will start with minus 1 by 2 plus 1 by 3 plus etc. plus 1 by n plus 1. Okay, so this is what you have. But if you look here, what happens is there's a minus here, you observe that, and this terms will get cancelled. Okay, so what remains is nothing but 1 minus 1 by n plus 1. Okay, and you can see that this is your Sn, and this partial terms partial sum is easily converges to 1, right? So the limit of the partial sum is nothing but 1. Okay, so that means your summation is actually 1. So this term, this is basically is equal to 1. Okay, so your series converges, but your root test and ratio test will not tells you anything. Okay, so just because root test and ratio test does not tells you anything does not means your series converges. Okay, and maybe here I will tell you a little bit more about this type of series. So something happens here, then what happens is you can kind of cancel out most of the things, and what remains is the first and last term, right? So this type of series are sometimes called a telescoping series. Okay. So if you are interested in jam or net exams or something, you probably look at a few more examples of telescoping series and work it out, because what happened in the exam, they used to see most of the series they give, not necessarily most of this, but yeah, many of the series what they give is in some sense telescoping series. If they want to, if they actually tell you, okay, what is the limit of the series, so if they actually tells you what is the limit, then you cannot use the ratio test or root test or nothing, right? Because that only tells you whether it converges or not. It will not tells you what is the limit. So if you want to use the limit, then you actually have to compute, and most of the time what happens is your series became some kind of telescoping series. So the idea is many of the terms will get cancelled and only a few terms survive, and whatever the terms survive, it may be easier to compute it. Okay, so we have done ratio test and root test. There is some integral test also, which I may not write here. Yeah. So maybe if you want, I can just write the statement here instead. Yeah. Okay. So basically, at least these are the main tests that we will use it, and there are many other tests are there, but I mean, you may not mostly don't use it. So if you want, you can also look into integral test. Okay, so this will be interesting one, but unfortunately, yeah. But anyway, so let's move on to alternating series. I want to go to the Taylor series. So let's see if I can finish the alternating series, then I can go to Taylor series. So you have a sequence. Let's say you have a sequence of this form. Okay, n equal to 1 to infinity minus 1 power n plus 1 un. Okay, but you have this un is a sequence of positive or non-negative terms. Okay. So if you have something like that, then this series is called alternating series. Okay. Then, so say a series is called. So if you want an example can be, one of the example is, as you said, it's, plus 1 minus 1, 1 minus 1, plus 1 minus 1, plus 1 minus 1. So similarly, you can go. This is, let's say, one example. Another example is, let's say, 1 minus 1 by 2 plus 1 by 3. Okay. So you have, two examples here. So let's go to the theorem here. And the theorem is the following. So the theorem tells you when your alternating series convergence. Okay. So it's called Leibniz theorem. Some people write lemma, but I write theorem. Leibniz test, some people write. So you have suppose un is a sequence of positive term. But the thing is, here you observe that, right? If you have a term like that, this series does not converge, right? You have said something. 7 o'clock, you have said something. This series converges to one. I hope you might have talked about this series. Okay. I mean, I missed your comment. Sorry about that. Okay, so we are doing the alternate series, but if you look at a series like this, 1 minus 1 plus 1 minus 1, then you can see this series does not converge anywhere, right? So in some sense, you don't want something like that. Okay, but I mean, I have told you that this series converges, and we will see. You need some more things for the convergence. Just the alternating is not enough for the convergence. You need more things, such that you have a decreasing series. Plus one for all. So maybe I will write it as a point by point so that it will be easier to understand. Okay. So the first thing is the series has to be monotonically decreasing.
100 rupees. What
What?
charge?
Okay. Just give me a minute. Okay. So there are few things that you need. The first one is the times has to be monotonically decreasing. The second one is it converges to zero. Okay, it's monotonically decreasing and it converges to zero as n tends to infinity. Okay. Then what happens is then summation n equal to 1 to infinity minus 1 power n plus 1 un converges. Okay. If the terms here has to satisfy the monotonically decreasing as well as it converges to zero, uh, then your alternating series converges. Okay. And you can see that is both is true for this series. Okay. And hence this series is uh, converges because of the Leibniz theorem. Okay, but we have seen that the series is not absolutely converges. Okay. Okay, and there are some absolute convergence here. Just give me a minute. I just want to see if there is something else here. So, have Sal done the rearrangement theorems? I don't know if the rearrangement is needed for whatever our course is. No, right? Okay. Because for our course, it is not really needed. Uh, but probably I will tell you what the theorem is. So maybe I'll write the theorem and just give some idea. I mean, I'm not going to prove it or see this Leibniz test we have, and one of the example is, let's say you can keep this as an example, okay? And we can give many example. All you have to check is these terms are monotonically decreasing, it goes to zero, then it converges. Okay, so any example that involves the alternating series, you always come back and check here. Okay. But let me tell something about this conditional convergence and absolute convergence, which it's not very necessary for our course because we are doing calculus, right? Not sequence and series, but it's nonetheless it's since we have done the something about this conditional convergence, etc. I will just tell you, and it's of course in most of the books you can look. Suppose you have this sequence n equal to 1 to infinity a n, and it is let's say conditionally converges. So conditional convergence means it is not absolutely convergent, but the series is convergent. Okay, so you only look at you have some series which is not absolutely convergent, but the series is convergent. Okay, so then it is called conditionally convergent. Then what you can do is then for all alpha belongs to R. So basically, you have a series, you have another series, not exactly an. There exists a sequence. So yeah, there exists a yeah, I'm writing sequence A n B n whose terms are obtained by so rearrangement of the terms of an such that summation equal to infinity bn is alpha. So what it tells you is suppose your sequence is conditionally convergent. Okay, now you have a series of terms an and you are looking at the sequence of term an and you are looking at the series of that, and it is conditionally convergent, so it's not absolutely convergent. Uh, then what happens is for any alpha, so basically what the question is, okay, if a series is a convergent, can I change the terms and it still be converges to the same limit? That is something one can think, right? Because here I have the series, let's say, and if I write this first, instead of writing like that, I write like 1 by 2 plus 1 plus 1 by 3 minus 1 by 4, and everything is same, but I just changing some terms here. uh, and the question is, okay, if we have some, that in a finite sum it is true, right? I can do any rearrangement and it is still true because you have some kind of commutativity there. The question is, does it true in the infinite series also? And the answer is, it is not true. And if you have absolutely convergence, it is true. So if your series is absolutely convergence, then whatever the rearrangement you do, you will your series will still be absolutely convergent and it converges to the same limit. Okay, but if you have a conditionally convergent series, then this is a theorem of Riemann, I think, if I'm correct. Uh, but what he proves is, for whatever the alpha may be, for whatever the real number you can take, there is always a rearrangement of your series of your terms here. So there is a rearrangement on these terms such that if you take the series of that, it goes to alpha. Okay? In some sense, it kind of tells you that if you have a conditionally convergent series, then the order in which that you add actually matters. Okay, if you change the order in which you add it, then you may not get the same limit. Okay, so that is exactly what this theorem tells you. Okay, so let's move on to uh, okay, why we are doing this all this sequence and series so far for our course where it's basically calculus. It's because of the following reason. There is something called Taylor series, but the story is it's all start in India in some sense. Uh, Not necessarily in the way that it is appear in the textbook, but there is a place called the Kerala School of Mathematics. I mean, it is now called as Kerala School of Mathematics. I mean, this is still I mean, this things are still working now, but not necessarily. I mean, there was a gap, and the government started it again. And there is a mathematician called Madhava. So what he does is he takes this sine and cos and everything, and he gave a series to it. What he is writing is, he says something like, if you have sine x, this is equal to, and he is giving a series. Okay, so for example, maybe I'll tell some examples here. So this will be etc. There's something like that. He is giving a series, and he has done for many things like sine, cos, tan, and even arc sine, arc tan. Some of them he has done it. I don't exactly know what he has done it, but at least for sine and cos, etc., he has done it. Okay. But this was like 250 years before the Isaac Newton, did whatever with the calculus. So this was like very early that he has some series. So what is interesting about this is you have some function and you can kind of able to see it as a polynomial. So in general, you can actually do. In general, the question is okay. If I have a differentiable function, can I see it as a polynomial? Okay, and that's where the Taylor series comes here. But I will tell you that there's a little problem here, but I will do it here. Okay, so you have a infinitely differentiable function. You need an infinitely differentiable function here, or some people call it a smooth function. Okay, then your Taylor series is nothing but summation f power n. I mean, when I write this f power n here, I will tell you what is f power n here by n factorial x minus a power n. Okay, and this series is called Taylor series. Okay, so what do you mean by f power n? So it is basically nth derivative. Okay, so f power n denotes nth derivative. So this is what is called as Taylor series, and if you put a equal to 0, then it is called Maclaurin series. Then so let me call this as T of x maybe for Taylor. Then T of x is called the Maclaurin series. Okay. So basically, yeah. So this term will kind of go away. Okay. I mean, this term not goes away, but this will go away, and this will be 0. Okay. So now the thing is, if you let's say if you want to okay, why it is interesting is sometimes what happens is your Taylor series will be actually equal to your function. Okay, but it's not always true. But there are situations in which for example sin x, cos x, and some of the interesting ones, your Taylor series will be equal to your function. Okay, and in general there is a some remainder. I mean, there is a theorem which is called the Taylor theorem, which tells you okay, if it is not equal, so what is the error, and it gives with some error. Probably I will write the Taylor theorem. I don't know if it is needed, but I can write the Taylor theorem here. Okay. I mean, forget it if it's not necessary. So first of all, the thing is this series need not to be convergent in general. Okay, and even if this series is convergent, that does not mean it has to equal to your f of x. Okay, but what happens is for some nice functions, this is actually equal to f of x, and that is what this Madhava etc. are doing. Somehow they are getting it, and you can see this is basically a Taylor series of sin x. Okay, for certain series it will be equal, and most of the trigonometric series it is equal, and for which these guys have already gave the series here. So in some sense whenever people tell, okay, they always say like Madhav also did some infinite series, and they will not give that much credit for what these guys did. And how many of you actually know even this guy's name? So do you know this guy's name? Have you heard of him before? Yeah, you might have heard, right? But sometimes people may not give the credit for what he did it, because see, once I see the series, I may, once I see something like that, I can. It's very natural for me to ask, okay, if we can do for sin x, can I do for the general f of x? And if somebody really smart, it's not easy, but if you're really smart and if you're somehow able to see these coefficients are coming from, let's say, uh, from your derivative, something like this, then it's not very it's not very hard to see that okay, I can write a series like this and see whether it is equal to your f of x. Okay, so this is basically exactly what Taylor is doing. uh, but I'm not telling what Taylor did is nothing interesting, but what I'm telling is the first time somebody see a function as a polynomial is not a trivial thing, and I think people does not give him enough credit for what he did it. While some people are telling that okay, this he did it, but then people are doing it independently. It's not very clear whether these things are independent or the idea transferred to Western world. These are not very clear. I mean, I can always say it's very independent. I can look at the book and say, okay, I still did by myself. So it's not very clear. But anyway, I'm not telling what Taylor, you know, did is something trivial. It is what he did is very interesting. But I'm telling that just this guy has done it even before that the calculus was formally introduced. Okay, so there's something about the calculus and different equations are all done in India, but not exactly. The real problem with India is they are not formalizing it, they are not abstracting it. They want to do some astronomy or whatever it is, and they are writing it inside, and they may be writing in some Sanskrit poems or something. Okay, it will be mostly appear as a poem. So for a average common person or for the knowledge to spread is not very easy. But when a Newton or somebody wrote it, and they wrote in a way that it's easy to easy for the knowledge to propagate. That was the only difference. But anyway, this is actually one of a significant achievement of this guy. But at least the idea that you can see a function as a polynomial, then this is a really nice idea. But anyway, so let's move here. So what Taylor says is your function is not exactly the same thing, but suppose if you have a f of x, which is a k times differentiable function, then what happens is your f of x is nothing but you have this Taylor term here, at least the partial sum in the Taylor term. By I factorial here. Minus a power I. Plus, there is something called some error term was there. X minus a power k. Okay. And thing about this error is this. This error goes to 0. Hk of x. So this goes to 0 as x goes to a. Okay. So it's not necessary that this function is the same as this, but he's saying it's the same as this up to some error, but this error goes to 0 here. Okay, and you can see here this there is also already x minus a terms comes here. Okay, so this goes to 0 much faster than x goes to 0 here, because here also there is something goes and here also you have, so the order is a little bit higher. Okay, okay, what do you mean by order? Don't ask me, but we can see that this term goes to x minus a much faster than x goes to a, because you can divide by x minus a and you can observe. Okay, if you take this term here, divide by x minus a, still this term goes to still this term goes to 0 as x goes to a. Okay, so in some sense this term goes to 0 faster than x goes to a. Okay, so this is the Taylor theorem. And this whatever this h of x, I mean, he just tells there exists a function h of x, and of course there are other theorems which kind of tells you, okay, you can tell me, okay, what is the h of x, but those are not very important for whatever the purposes that we are doing it. But one can give the explicit formula for this remainder, at least in some sense. Okay. Okay, but in general, this Taylor series by here, when I write the Taylor series, this will be n goes from 1 to infinity, because it's a infinitely differential function. This Taylor series is not necessarily even convergent, and even if it is convergent, it does not necessarily converges to your f of x. Okay, so that was the thing. But for some nice functions, this converges. So maybe we'll give some examples, and then we can proceed with some problems. Okay, the problems are the interesting ones, but we'll give just some example. Okay, I don't remember the. I mean, I don't exactly remember all the examples, so I will look through my notes and I will tell the examples. So give me 1 minute. So I will look through my notes and then I will tell the example. Okay, so I got this. So you have some examples here. So if you want to look at sine x, this is nothing but x minus x cubed by 3 factorial plus x power 5 by 5 factorial plus etc. And you can give the general term. If you want, you can give the general term. This is nothing but summation n equal to 0 to infinity minus 1 power n by 2n plus 1 factorial x power 2n plus 1. Okay. And similarly, you can give for cos x. It's nothing but 1 minus x square by 2 factorial plus x power 4 by 4 factorial plus etc. And you can do for tan x. This is x plus x power 3 by 3 plus 2x power 5 by 15 plus etc. Okay, here how this terms comes. Okay, at least till here you can generalize it, but here these coefficients are a little bit tricky. There's something called the Bernoulli numbers, and you need to do those things. Okay, so it's not yeah, it's not as generalized like this. But anyway, for whatever our purposes, we don't need much here. All you need to know is these terms are higher order. Okay, they will be of order x power 7 and so on. Okay, so that is all more or less you need it. Okay, similarly, you can say for secant functions, etc. And logarithmic also there are formulas. So anyway, the formulas you can look up. So now let's move on to one problem, at least a few problems. Let's see if it's possible. So let's do a few problems. So first one is, let's say we compute limit uh, x tends to 0. Let's say sine x by x. Okay, we know this is 1, but let's apply the Taylor series and compute. Okay, so this is one example that you can do. Okay. So this will be, we will apply the Taylor series here. I will copy here. And I will go and paste it here. Okay. This divided by x. So this is nothing but x minus x squared by 3 factorial plus x power 4 by 5 factorial plus etc. So as are not x, this is 1. Okay, so this is what you have. Now what you are going to do is you have to apply the limit x as x goes to infinity. Limit x goes to 0. You have to see it. Okay, so these terms are terms that involves h, or some people may like to write it something like limit x tends to 0, 1 plus order of x square. Okay, so what does it mean by order of x square? Is all the term has order at least x square. Okay, and as x goes to 0, this term will goes to 0, and what remains is just nothing but just 1. Okay, so yeah, so that is pretty much it. So you can do some things like that here, but one thing you observe, one thing I want to see is you're taking the summation first, right? And then you are applying the limit. Okay, now the question is, can you split into each of this limit? Okay, so basically the question is, can you flip the sum and the limit? So this kind of problems are there, but it will be fine, because for finite thing you can do it, and you can just and the series is nothing but the limit of whatever it is. Okay, so these questions are there, but yeah, but you can do it. Okay, so maybe let me do one more problem here. So this problem is, let's say, tan x minus 1 by let's say 2x. Okay, I mean the similar problem is in the assignment, but so I'm not going to prove it. Anyway, I'll put this problem. So I will not do fully here because it's in the assignment, so I don't want to do here. I'll just give you the hint. So what you do is, don't try to apply the tan directly here. Okay. One thing what you can do is you can apply tan directly here, but if you apply, you see what happens. So here you have a term like this, and that is going to come in the denominator. And how do you deal with that? That's not very easy. So instead, what you do is, I mean, there's a term here in the denominator is not the serious issue. The serious issue is you have a term in the denominator, as well as you are subtracting something, right? And how do you, compare these two? So what you do is, first you just uh, cross multiply and simplify it by x tan x. Okay. Now what you do is, now you apply Taylor series for both of this. Okay, and then play around. You will get the answer. Okay, I'm not going to do the problem, but if you play around sufficiently enough, then you will get it. Okay, maybe we'll just do it. It's fine. Do you want to do it or not? I don't know. Hmm. I don't know if you want to do it or not. Yeah, maybe I will not do it because it's a exercise problem. But now you can try to apply the Taylor series, and you can kind of get it. Okay, so one can do more problems of this form. So maybe give me 1 minute, and I will see if there is some other interesting problems as well. Yeah, so these are the ones, but yeah. So the assignment has a lot of questions are there, but I think whatever the tools we gave will be enough for you guys to solve it, is what I was hoping. I don't know there is anything that's significantly harder there. Uh, yeah, I hope you can able to solve it. For example, okay, we will do maybe one such problem, uh, and then we'll solve it. Okay, something like this is there, right? N equal to 1 to infinity, 1 by root n minus 1 by root n plus 1. So how do you solve this type of problems? So these are just, I mean, this is one problem from the assignment I'm just taking. I'm just taking the hard ones, not the easy ones. And of course, I will not solve it completely for sure. But if there's hard, I can just give some hint. That's all. Because we have seen similar kind of problems, right? At least one problem we have seen it. It just the same thing. You just have to see that it's the same thing. So it might looks hard, but what happens here is you write both of the terms, okay, and then you can clearly see these are just the same terms. So if you write it, what you get is so this is 1 by root n, right? So maybe we'll write here 1 by root n. This is it square root of n plus 1 square root of n plus no square root of n, yeah. Yeah, okay. Sorry about the doubt, yeah. Yeah, square root of n plus 1, then it will be hard, I understand. Square root of n plus 1 is much simpler. No, it's not exactly like this, but yeah. 1 minus 1 by root 2 plus 1 by root 2 minus 1 by root 3 plus 1 by root 3 minus 1 by root 4 plus dot plus. So I'm looking at the nth term. Okay, so this will be plus 1 by root n minus 1 by root n plus 1, right? You have only something like this. Now, clearly what you can do is you can strike out these terms, right? You can strike out all of these terms till here, and what remains is nothing but just two terms. Okay. And so this is your lesson, and you just apply the limit. So here there is no issue with the rearrangement because you are only taking the finite sums, and whenever you do the finite sum, you can rearrange. That's not a problem. Only the problem comes is when you have infinite sums, and then you cannot directly rearrange as long as this sequence is not absolutely convergent, then you cannot rearrange. Again, if you have a term of positive series, then you can rearrange. It doesn't matter because if you have a term of positive series and you rearrange it and it become convergent, then it means that series is absolute convergence and any rearrangement is fine. So that will not be a problem. But when you don't have a term of positive series, you cannot rearrange if you have infinite series. But now I am looking at the finite sum, right? So I'm taking till only nth term. Here I can rearrange. However I want to move it, it's fine. So yeah. So most of these problems will go like this, and I don't think there is any really hard problem is not here. Let me just give me 1 minute. I will just see if there is any other hard problems. Yeah. Okay. I don't know. I don't think there is any other hard problems, but yeah. Okay. Do you have any doubts? Then we can discuss. Otherwise, we can end the class. Yeah, and Okay, there's no doubt. Okay, we'll end the class, and by the way, all the best for your exams. Yeah. So that's all. So when is the exam though? I hope it might be announced, right? You haven't registered for the exam, okay? I mean, you could have registered because sometimes you can use this grades for your class. Actually, I don't know if your institute allows it, but you can ask them. Sometimes you can instead of creating one course in your college, you can create one course in NPTEL. At least some universities allows it. So I mean, next time, yeah, yeah. I mean, if they give credit for that, then it is good, right? Because anyway, you are attending all the classes, etc. So it will be useful. Yeah. So, so at least do you got the idea of what we are doing in you know this class per se? Like I mean, for whatever the course you studied. So what is more important? I mean, some of these problems are there here and there is nice. Some tricks are there, but you should understand what is the bigger picture. What exactly happened so far? Have you able to see that? Yeah. So if you want, you can just tell what it is. Foundations of Seki. Oh, like foundations mean what kind of foundations? You can open the mic if you want.
Hello.
Oh yeah.
Yes, like I haven't proved like everything rigorously and I don't know what goes behind the scene.
Behind the scene means the proofs you are telling.
Yes,
Okay, some proof you can look. I mean, if there is some proof, if you find it hard, at some point you can skip it and come back. It's not the end of the world if you don't understand one proof. For example, let's say there's a theorem. Let's say the fundamental theorem of calculus. You don't understand the proof, let's say, but of course the statement is at least one should understand, and I think you can understand the statement. If you don't
yes,
understand the proof, it's not like okay, that's all. No, you can come back to it. You go forward, go and do something more, and then when you come back you can clearly say, oh, this is how it is. Sometimes the
yes,
idea
that's
comes a little later.
yes, that's why I started real analysis.
Okay, you can do real analysis, but see, the only difference between calculus and real analysis is real analysis is a little bit more rigorous, but on the other hand, I feel calculus is, it gives you more intuition. So, in some sense, the intuition is actually one of the very important thing. Because the later when you do, advanced theories, etc., the intuition will not be that much there. For example, here also you do sequence and series. Uh, of course, there's a different type of analytical intuitions are there, but not necessarily a pictorial intuition, right? For
Yes,
example, when you do the Zeno paradox, you can always, you said the Zeno series, right? You can see it as some geometric problem, right?
yes,
So if you have a square here, uh, and you see the area of the square is one, right? If I put it's a unit square, let's say it's not looks like a square, but yeah, let's say it's a unit square. Okay, and if you want to find the summation 1 by 2 power n, this is nothing but the first term is the half, second term is 1 by 4th, and third term is 1 by 8th, fourth term is 1 by 16, and then you can do like this, right? By
yes,
doing that, the sum of all of this term is nothing but one. You can do some geometry here in the at least in the early stage. Similarly, calculus you can do a lot of geometry, but after you go further, you may not able to do that much geometry. But these ideas are actually very interesting. So what you can do is try to get the intuition. That is, I would say, more important. At least whenever you do calculus, have a feeling for what is the the limit, the derivative, etc. So you should have developed some intuition, and you have to feel that somehow whatever happening is correct. Okay, so I mean, I feel that is like more important in calculus. Proofs, if you don't understand a little bit of the proof, it is fine. You can always come back and check again. So that don't
like
worry about much.
when I don't understand, like a thing to that I feel very uncomfortable.
No, no. See, okay, I will tell you. I have seen two type of people. Okay, there are people. If a paper somebody claimed, okay, this is true. Some people cannot just accept it. Okay, unless they see the proof, they simply don't want to accept that this is the truth. That can be good, but it can also be bad because now you are stuck in that, right? And you cannot go further. So at some point, what you do is, okay, you don't understand, you remember it, you come back. Okay, so don't stop there because if you stop there, then you may not able to do much. So if everything you wants to complete only, then I move forward, then that is may not going to happen because sometimes what happens is sometimes some things will take time. For example, I will tell you one example. Suppose you have a computer here, okay, and you are running some 10 tasks inside this computer. Okay, let's say this computer has some 8 core or something and it can run 8 tasks there. Okay, but one task you gave a very heavy task. Okay, and okay, but now what you're doing is you just want to open some text file because you want to scroll through it, but your computer says, hey, I will not open my your text file because I'm doing a heavy task here. Do you be happy about that?
No,
So what you want your computer to do is it should do the heavy task with whatever the computing force. But if I gave some simple task come in, you should perform the simple task quickly and then go back to the heavy task, right? So maybe
yes,
you can take some inspiration from the computer. If you see some theorem is hard and you are not able to get it, it is okay. I mean, you try it, but then you do the other things also in the side, and then at some point you will get it. But if you stuck with that and if you tell only after you finish it I move, that's not going to work. I mean, I don't know if that is how you do it, but I'm just telling.
I think moving on is important.
Yeah, at some point you have to move on, but you can always remember, right? You can always remember and come back, and some point you can finish it. But if you stay there, you might able to do it in 3 months or some, or maybe not 3 months, maybe 1 or 2 days also you can do it. Uh, but the thing is that 1 or 2 day you can do something, and this will naturally comes in the second day. Okay, and another thing you should understand is your brain takes some times to get observe the things. So we study today, you cannot expect your brain to suddenly get the ideas tomorrow, but give it enough time
Yes,
also.
not only I gave a lot of stupid answers to them. So
What answer?
like the wrong answers, they were a bit too stupid.
Why?
Like
See,
they were wrong because
you're telling that if you give wrong answer it is bad.
yes, sometimes.
See, what I would tell you is, when you think, okay, the first time whatever you think, you may not know for sure that it is right or wrong. Okay, you might have idea this could be right. Okay, but you have to go and verify it. And sometimes whatever you think may not be true. Okay, then that is very very natural. In some sense, what should be what could be a serious problem is that you write something and you believe this is right, and you were not able to figure out whether it's right or wrong. I mean, some people are there, uh, they think what they think is right and they don't know that. See, not knowing is not a problem, but not knowing that what you did is wrong is a problem. Not doing wrong is also not a problem, but you should figure out that is a wrong. As long as you have that one, it's not a problem. See, you write something, right? I mean, I have seen a few minutes back you said something, but after a while you just told, okay, it is wrong, right? So you
Yes,
figured it out, and that is all that it's needed.
yes,
Okay, so I mean, everybody will be wrong. It's not the first time whatever you say should always be right. I mean, that's too much to expect. Uh, but what
yes,
is necessary is to have the ability to figure out when you make a mistake, you should be able to figure out that it is a mistake. The quicker you can able to do it, the better it is. So don't worry if you make one or two mistake. That always makes, okay. See, even when I teach, you can see, right? So I makes this. See, my mistakes are very, super. I wouldn't say it's superficial, but it's very stupid. I miss a minus, I miss a plus, or I miss something like that. Okay. Uh,
Yes,
people,
but it is not a big mistake, right? It is not like a
people
fundamental mistake.
people say it's a silly mistake, but it's not silly when you do it in the exam. Okay, not necessarily only in the exam. When you do a research paper or something, these are not. I mean, if you just because of that you got something which is not supposed to be, then it's not a thing, right? You have to be careful. So some people might have some issues. It's not necessarily something that spoils of whatever. I mean, there will always be some problem. Okay, at least in my case, I have this, and I don't know how to fix it. Okay, it's not like I don't want to fix it, or I didn't try to fix it. I tried it, but it's not always easy. So what I realize is, okay, when it happens, I will just recheck it once again. So when you recheck it once again, the chance of you making it, the probability is very low. So it's okay, but I mean, you don't have to think too much about that. Yeah, as long as you can able to figure it
Yes,
out, and you should be have a technique to figure it out, you're fine.
yes. So
Because
I have some doubts in real analysis. Can I ask?
yeah, yeah, okay. We may stop this lecture and you can ask. Yeah. Okay then. All the best for the class, and yeah, we'll see you.